You look around at the world on any given day, right? Like a bustling city street packed with cabs.
Oh, yeah, just pure noise and movement.
Exactly. Or, a crowded hockey rink with bodies slamming into the glass. Or even just your own kitchen when you accidentally drop a stack of ceramic plates onto a tile floor.
Which is always a disaster.
It's the worst. But it all looks so incredibly chaotic. I mean, it feels like a million different things are just happening randomly. Pure, unadulterated anarchy.
It certainly presents that way to our eyes, yeah. I mean, things crashing, spinning, splintering apart, they bounce off one another at completely unpredictable angles.
Right.
It's overwhelming to process. So we just accept that things break, things fall, and chaos is just the natural baseline of reality.
Right. Chaos is just a Tuesday morning. But when you look through the lens of pure physics, that chaos completely evaporates.
It really does.
You realize you aren't looking at anarchy at all. You are looking at, a perfectly balanced spreadsheet. Every single motion, every bounce, every shattered piece of ceramic is accounted for. It is the ultimate unbreakable ledger of the universe.
And exploring that ledger is our mission for this deep dive.
Yes, it is.
But the goal here is to completely change how you, and we really do mean you listening right now, how you view every single physical interaction in your daily life.
Yeah.
We're talking about the hidden, unbreakable ledgers of motion that govern everything. From dropping a set of keys in your driveway, to driving a car on a perfectly frictionless icy road, to watching a figure skater pull off a dizzying spin.
Okay, let's unpack this. Because to actually see this universal ledger, we have to understand the currency that it trades in.
The currency of motion.
Exactly. And in the realm of physics, that currency is momentum. The manuscript lays out this fundamental equation right at the start. It says, momentum equals mass times velocity. Mass and velocity multiplied together.
It sounds like a really simple algebraic formula.
Right, times dollar.
Yeah, but it represents something profound about physical reality. It is the true measure of the total motion of a body.
To make this incredibly concrete, think about trying to stop a physical object that's moving directly toward you.
Okay.
If you have a baseball tossed to you gently, meaning it has a low velocity, you can just stick your hand out and catch it.
Right. It requires very little effort to stop.
Exactly. But if that exact same baseball is fired out of a mechanical pitching machine at 100 miles an hour, a massive increase in velocity, it requires a tremendous amount of effort to stop. If you don't use a padded glove, it's going to do some serious damage.
Oh, absolutely.
So an increase in velocity drastically adds to the total motion of the object.
That covers the velocity side of the equation. But now, keep the velocity exactly the same and alter the mass.
Okay.
Imagine that baseball rolling toward you across a driveway at a slow, lazy, 5 miles an hour. You stop it by just putting your foot in its path. Easy.
Barely feel it.
Right. Now imagine a heavy bowling ball rolling towards you at that exact same 5 miles an hour.
Oh, yeah. You wouldn't just casually stick your toe out.
No, it would hurt. And if you scale that up to a massive granite boulder rolling at 5 miles an hour, it will completely crush you. The speed didn't change at all, but the massive increase in mass fundamentally changed the amount of motion you had to deal with.
Which proves that both mass and velocity are completely equal contributors to this concept of total motion. You can't just look at how fast something is going to judge its impact.
Right.
And you can't just look at how heavy it is. You have to multiply them together. That mathematical product is momentum.
And understanding momentum as a currency naturally brings us to a crucial companion concept, which is impulse.
Impulse.
Yeah. If momentum is the currency of the universe, impulse is the transaction.
I really like that framing. Impulse is the transaction. So how exactly does that transaction work?
Well, impulse is defined as force multiplied by time. So if you apply a physical force to an object and you sustain that push for a certain amount of time, you are applying an impulse to it.
Okay.
And here's the golden rule of mechanics. Applying an impulse to a body at rest gives it a momentum exactly equal to that impulse.
Wait, exactly equal?
Exactly. Or if the object is already moving, the impulse you apply equals the exact change in its momentum.
Let me visualize this. If I'm at the grocery store and I push a heavy shopping cart down the aisle, the actual physical force of my muscles pushing, multiplied by the number of seconds I spend keeping my hands on the handle and pushing,
Right.
that translates perfectly into the mass of the cart, multiplied by the speed it gains.
Precisely. And for those who appreciate the underlying elegance of mathematics, the proof of this perfect translation is in the units themselves. It is incredibly satisfying to break down.
Let's do it.
Let's look at the standard metric system, the MKS system. which stands for meters, kilograms, and seconds.
Let's walk through the math, because this blew my mind when I realized how perfectly it aligns.
Think about force. Force is measured in newtons. But what is a newton in physical terms?
Right, what does it actually mean?
A newton is explicitly defined as the exact amount of force needed to accelerate 1 kilogram of mass at a rate of 1 meter per second every second.
Okay.
So a newton is literally a kilogram meter per second squared.
Okay, a newton is a kilogram meter per second squared. That's the force part of the equation.
Right. Now remember our definition. Impulse is force multiplied by time. So we take that newton, our kilogram meter per second squared, and we multiply it by time, which is measured in seconds.
So mathematically, when you multiply by seconds, it cancels out one of the seconds in the per second squared denominator of the force.
Exactly. You are left with a new unit, kilogram meters per second. But consider what the units are for our currency, momentum.
Oh, I see where this is going.
Momentum is mass times velocity. Mass is measured in kilograms. Velocity is measured in meters per second. Multiply them together, and what do you get?
Kilogram meters per second.
Kilogram meters per second.
It's identical.
They are the same.
So mathematically, the effort it takes to push something over a specific duration of time, the impulse, is literally constructed of the exact same mathematical stuff as the object's physical weight and speed once it's rolling away from you.
They aren't just related, they are identically measured.
They are the same thing expressed in different states. Impulse equals the change in momentum.
It is a perfect, flawless one-to-one exchange. The universe keeps absolutely perfect books. Every drop of effort you put in translates directly into the currency of motion.
That is just wild to me. It's not a metaphor. It's the mathematical reality of the physical world.
Yes.
But if impulse and momentum are a perfect exchange, like a strict accounting system, what actually happens when two moving objects meet and try to trade this currency? What happens when they collide?
This is where we enter the realm of the unbreakable ledger, the law of conservation of linear momentum.
To picture this, let's look at an incredibly vivid thought experiment from the source. Imagine two hockey pucks.
Perfect example.
They're identical. They have the exact same mass. And they are speeding across a perfectly frictionless sheet of ice, heading directly toward each other at the exact same speed.
Now, before they actually hit each other, we have to talk about vectors. This is a critical distinction. Momentum is not just a raw amount of motion. It has a very specific direction. It is a vector quantity.
Right, because velocity has a direction. Speed is just how fast you are traveling in a car. But velocity is how fast you're traveling and whether you are heading straight north or straight south.
Exactly. So let's assign directions. The puck sliding to the right has a positive velocity. Therefore, its momentum is a positive number.
Makes sense.
The puck sliding to the left has a negative velocity. Its momentum is a negative number. Because their masses and speeds are identical, their momentums are exact opposites.
So if we look at the total system, both pucks existing together on this ice, we add the positive momentum and the negative momentum together. The total momentum of our little hockey rink universe is exactly zero.
Keep that zero firmly in mind. It is the baseline of our ledger. Now, let's run the first scenario, which physicists call an inelastic collision.
Okay, so imagine we take both of these hockey pucks and rim them with industrial strength superglue.
Right.
They slide toward each other, they hit head on, and smack. They instantly adhere to each other. Because they hit with equal force, they come to a dead, immediate halt right in the dead center of the ice.
And the instinctual question anyone would ask is, has the momentum been destroyed? We just witnessed all this violent high-speed motion, and now we are looking at a completely stationary lump of rubber.
It certainly feels like the motion was violently killed. I mean, they were flying, and now they are completely stopped.
But look at the ledger. Before the collision, we had a positive momentum plus a negative momentum of the exact same value. They summed to zero. After the collision, the stuck-together pucks are not moving at all. Their final velocity is zero. And anything multiplied by zero is zero.
Right.
The ledger was zero before they hit. The ledger is exactly zero after they hit. The momentum wasn't destroyed. It was simply perfectly canceled out. The ledger remains balanced.
Okay, that's what happens when they stick together. What about an elastic collision?
Let's hear it.
Let's say there is no glue this time. The pucks are made of a perfectly bouncy, spring-like material. They hit head-on and violently bounce off each other, reversing direction.
The math here is incredibly satisfying. The first puck, which came in with a positive momentum, bounces back the way it came. It reverses its direction completely, so its new momentum becomes negative.
And the second puck, which was coming in with a negative momentum, bounces back the other way, so its new momentum becomes positive.
Yes. They simply traded ledgers, they swapped momenta. So instead of the total system being positive plus negative, it is now negative plus positive. The total mathematical sum of the system remains exactly 0. The ledger is perfectly balanced once again.
Let's push this concept further because it gets really fascinating when the scenarios get messy. What if the pucks don't meet in a perfect, straight line, head-on crash? What if it's a glancing blow?
The universal rule holds firm. If they meet at a messy angle, their velocities aren't in exactly opposite one-dimensional directions anymore. You can't just use simple addition and subtraction.
Right, because they're flying off at weird angles.
Exactly. You have to use two-dimensional vector addition. You draw geometric arrows representing their momentums. The length of the arrow is the mass and speed. The angle is the direction. You add those geometrical arrows up, and the total invisible vector before the crash will perfectly, flawlessly match the total vector after they bounce away from each other into the corners of the rink.
It even works if one puck is just sitting still. If a moving puck strikes a stationary puck at a glancing angle, the resting puck suddenly darts off, and the striking puck veers off its original path. But if you take their two new angled momentums and add them together geometrically, the resulting line perfectly matches the exact straight line momentum of that first puck right before the hit. The motion just splintered, but it didn't change its total value.
Let's make it even more challenging. Let's abandon the identical pucks and look at unequal masses.
This thought experiment really solidified the concept for me. Let's say one puck is normal size. It's moving to the right at a certain speed. It has a baseline positive momentum.
Okay.
And sliding toward it from the other side of the ice is a giant puck. Let's say it has exactly 3 times the mass of the normal puck.
A huge one.
Right. And it's moving at the exact same speed, but to the left. Because it's 3 times heavier and moving left, its momentum is negative 3 times the baseline.
So let's check the ledger before the crash. We have a positive 1 from the small puck plus a negative 3 from the giant puck.
Yeah.
The total system momentum is negative 2.
Now, let's apply the super glue again. They hit head-on and stick together into one massive clump. What happens?
Well, common sense, and anyone who has ever watched a football game knows the giant puck is going to win that interaction.
Absolutely.
It's going to plow right through the little one and keep going left.
It absolutely does plow through, but physics tells us exactly how fast it plows through. After they stick, they form a new, unified megapuck. The mass of this new object is the small puck's mass plus the giant puck's mass, 1 plus 3. The new total mass is 4.
Okay, the combined mass is 4. But what is their new velocity as they slide together?
Well, we know the final momentum must equal the initial momentum. The universal ledger demands it. The initial momentum of the system was -2. So our new megapuck with a mass of 4 must have a velocity that makes the total multiplication equal -2.
It's basic algebra at that point. 4 times what equals -2?
I don't know, it has to be -1/2.
Exactly. The combined pucks will continue moving to the left. That's the negative direction.
Right.
But at exactly half the original velocity. And if you multiply a mass of 4 by a velocity of -1/2, you get a final momentum of -2.
The starting momentum was -2.
And the final momentum is -2.
Yeah.
The law holds flawlessly. It is completely unbreakable.
It's almost eerie how perfectly the math dictates the physical reality.
It is.
But what about situations where momentum seems to be created out of absolutely nothing? Because the ultimate example of this is firing a bullet from a gun.
That is a brilliant example to explore. Picture a rifle loaded with a bullet, just resting flat on a wooden table. Neither the gun nor the bullet is moving. The total momentum of this entire system is exactly 0.
Then you pull the trigger, the gunpowder violently explodes. Suddenly, you have a bullet flying out of the barrel to the right at a massive supersonic velocity. It possesses a very real, very dangerous positive momentum.
Yes, it does.
It went from a 0 state to a huge positive number in a fraction of a second. Doesn't that mean we just spontaneously created momentum? Haven't we finally broken the ledger?
We only broke it if we made the mistake of drawing our boundary too small. We forgot the rest of the system.
Oh.
The flying bullet is only 1/2 of the equation. The other part is the gun itself. If the bullet suddenly gains a massive positive momentum, the universe strictly demands that something else must instantaneously gain the exact same amount of negative momentum to balance the books back to absolute 0.
And that something else is the heavy metal of the gun itself.
Precisely. The gun must move in the exact opposite direction. This is the physical reality of what we feel as recoil. When a hunter fires a rifle and it kicks back brutally into their shoulder, that backward jerk is literally the universe violently balancing the momentum equation back to zero.
And the math of the recoil is fascinating. If the gun is physically much heavier than the little bullet, let's say the gun has 100 times the mass of the bullet, it must move backward with exactly 1/100th of the bullet's velocity.
Because 100 times the mass multiplied by 1/100th of the velocity perfectly equals the mass and velocity of the bullet, just in the negative direction.
Right.
The total momentum of the gun plus the bullet is zero while it sits on the table, and it is exactly zero a millisecond after the gunpowder explodes. The distribution of the motion changed wildly, but the ledger remains pristine.
Which brings us to a really profound realization. This universal ledger is incredibly strict. Every single experiment, every crash, every explosion we can devise brings us to the exact same conclusion. The total momentum of an isolated system of bodies remains entirely constant.
That is the formal, defining statement of the law of conservation of momentum. To conserve something means to protect it, to guard it, to keep it safe from loss or spontaneous creation. The universe fiercely, perfectly guards its total momentum.
But contemplating this strict accounting system makes you wonder, who actually figured this out? Who realized the universe was operating like an accountant? I think most people, myself included, would immediately assume it was Isaac Newton.
Oh, almost everyone assumes that.
Right. When you think of the fundamental rules of physical motion, Newton is the name that comes to mind. But there's a historical and philosophical twist here in the source material that is just brilliant.
It is a wonderful piece of scientific history. What's fascinating here is that the law of conservation of momentum was actually formally published by an English mathematician named John Wallis, and he published it in 1671.
Wow.
That is a full 12 years before Isaac Newton published his famous Principia Mathematica and his 3 laws of motion.
12 years. John Wallis beat the most famous physicist in history by over a decade. You constantly hear about Newton's third law. For every action, there is an equal and opposite reaction. But Wallis was sitting there 12 years earlier saying, look at the math, the ledger is always perfectly balanced.
And here is where the physics and the history interlock so beautifully. You could actually derive the law of conservation of momentum directly from Newton's third law. They're two sides of the exact same coin.
How does that derivation work in practice, like mechanically?
Let's go back to our 2 colliding bodies. At the exact microscopic moment they make physical contact, body A exerts a crushing force on body B. Let's call it force F. According to Newton's third law, body B must exert an equal and opposite force back onto body A, so negative F.
Equal and opposite force. That makes intuitive sense.
Now, they are only exerting this extreme force while they are in actual physical contact with each other. And the time they spend in contact must be exactly the same for both of them. Body A cannot physically touch body B for a longer duration than body B touches body A.
Well, yeah, obviously.
So the time of the crash, T, is identical for both.
Right, a collision is a mutual shared event in time.
So think back to our definition of impulse. What is the impulse body A exerts on body B? It's the force multiplied by the time, F times T.
Okay.
And what is the impulse body B exerts on body A? It's the negative force multiplied by the same time, negative F times T.
And as we established earlier, impulse is the exact same thing as a change in momentum.
Exactly. The impulse of F times T gives body B a specific change in momentum. Let's say it gains positive motion. The impulse of negative F times T gives body A the exact opposite change in momentum. It gains negative motion.
Right.
Whatever momentum one body gains from the crash, the other body mathematically must lose. The total momentum of the system must remain exactly the same as it was before they touched. We have just logically proven the conservation of momentum using Newton's third law as the starting point.
Wait, let me push back on this because this feels like a logical trap.
Okay, go ahead.
If Wallis figured out conservation 12 years before Newton, then couldn't you just work the entire logic backward? Couldn't you start by saying, because we know momentum is conserved, therefore every action must have an equal and opposite reaction?
You absolutely can. You can derive Newton's third law from the conservation of momentum just as easily as you can do the reverse.
But if physicists can use the third law to prove conservation, and then turn around and use conservation to prove the third law, aren't they just arguing in a giant circle? Isn't that just a logical loop where they aren't actually proving any fundamental truth at all?
It looks like circular reasoning on the surface, yes. But it actually reveals a very deep truth about the philosophy of science itself. Science is not always a matter of proving an absolute, divine truth handed down from above.
Then what is it?
It is often about making a fundamental assumption based on observation and then demonstrating the logical consequences of that assumption.
So it's about building a framework that just consistently works.
Yes. You can choose to start by assuming Newton's third law is the fundamental truth and logically show that conservation of momentum must follow. Or you can start by assuming conservation of momentum is the core truth and show that the third law is an unavoidable consequence. The direction you move through the logic is just a matter of mathematical convenience.
But there's no absolute proof that the foundation itself is true.
In a strict philosophical sense, no. You cannot prove a universal generalization just by running experiments. You could run 1 billion successful collision experiments in a lab where momentum is perfectly conserved. But you can never philosophically prove that the 1,000,001st experiment tomorrow won't spontaneously break the rule.
That is slightly terrifying, to realize the foundation of physics is just waiting to be proven wrong.
The entire structure of classical mechanics rests on a single empirical reality. No human being in nearly 3 centuries of testing has ever been able to produce a clear-cut, reproducible demonstration of an isolated system where the third law or the conservation of momentum is disobeyed.
Wow.
The law rests entirely on a complete lack of exceptions. If tomorrow someone builds a machine that clearly breaks the ledger, the entire foundation of physics would have to be fundamentally rewritten.
That is thrilling. But to play devil's advocate, I want to try to break the law right now. I'm going to present a scenario that feels like a cheat code to break the universe's ledger.
I welcome the challenge. Let's hear it.
Okay, I am playing a game of pool. I hit a heavy billiard ball squarely toward the cushion, the rim of the table. It hits the rail, and it bounces straight back along the exact same line it came from. Its velocity was positive, now it's negative. Its momentum completely reverse direction.
Correct. You have a clear, massive change in the net momentum of that billiard ball.
But it didn't hit another ball. It didn't swap momentum with a second moving object. It just hit a stationary rubber wall and reversed. The momentum of the ball changed completely, but absolutely nothing else started moving to balance the ledger. I created a change in momentum without an equal and opposite reaction. I broke the law.
You didn't break the law. You just drew the boundary of your system far too small. You were looking at the trick through a pinhole. The billiard ball does not represent the entire isolated system.
Okay, so what constitutes the rest of the system? The pool table itself.
Yes, the heavy billiard table exerted the massive impulse that altered the ball's momentum. So according to the ledger, the table must have absorbed that exact amount of momentum in the opposite direction.
But the table didn't physically move. It's incredibly heavy. It's just sitting there dead still in the middle of the pub.
But why isn't it visibly moving? Because the legs of the table are fixed to the floor by frictional forces that are way too strong for a tiny billiard ball to overcome.
Right.
And the floor is permanently attached to the foundation of the building. And the foundation of the building is embedded deep into the planet Earth. When that billiard ball hits the rail and violently changes its momentum from positive to negative, the momentum of the entire planet Earth changes just enough to completely compensate for it.
You cannot be serious. Are you literally saying that by playing a game of pool, I am physically moving the planet?
Mathematically and physically, yes. The momentum of the Earth shifts to exactly cancel out the change in the billiard ball.
That is wow.
However, the mass of the Earth is astronomically incomprehensibly large. It is roughly 6 × 10⁻⁴ kilograms. Because the Earth's mass is so massively huge compared to a half-pound billiard ball, the Earth's resulting change in velocity is correspondingly microscopic.
So we just can't feel it.
Right. It is far, far too small to ever be detected by any human instrument that currently exists or ever will exist. But mathematically, universally, the Earth moved.
That fundamentally alters how I view everyday actions. Think about dropping your phone. As your phone slips out of your hand and falls toward the floor, gravity is accelerating it. It's picking up speed, which means it is rapidly gaining downward momentum. If the universal ledger is truly unbreakable, that means...
And it means the Earth must gain the exact same amount of upward momentum. The Earth must literally rise up to meet your falling phone.
That is just staggering to visualize. The entire globe shifting upward to catch my dropped phone.
It is the absolute truth of the physics. The gravitational force isn't just pulling the phone down toward the ground. It is a mutual attraction pulling the phone and the entire Earth toward each other.
Right, because gravity works both ways.
Because the Earth's mass is so incomprehensibly huge, its upward acceleration toward the phone is vanishingly, infinitesimally small. We completely ignore it in practical everyday calculations because it has no bearing on our lives. But the principle remains absolute. Motion is never created out of nothing when a body falls.
Wow.
The downward motion of your phone and the microscopic upward anti-motion of the Earth are both produced simultaneously, and they perfectly, flawlessly cancel each other out in the ledger.
So the total momentum of the Earth and the falling phone, when calculated together as a system, is exactly 0 before you drop it, 0 after it smashes on the floor, and exactly 0 at every single microscopic fraction of a millisecond while it is falling through the air.
That is the unbreakable ledger. It governs the cosmic scale of planets and the everyday scale of dropped keys. No amount of internal interaction among the parts of a closed system can ever alter the total momentum of that system.
It makes you feel deeply connected to the physical environment in a way we usually ignore. But up to this point, we've only really been talking about things moving in straight lines. Falling straight down, sliding straight across ice, flying in an arc through the air.
Right.
This kind of movement is called translational motion.
Yes. Translational motion is when an object is displaced through physical space as a whole unit. You physically translate from point A to point B.
But what happens when an object is bolted down and physically cannot move in a linear direction? What if it's permanently fixed in place? It can't translate through space, but it can spin. Which brings us to the fascinating twist in our physics journey: rotational motion.
Rotational motion is completely captivating because it is deeply analogous to straight-line motion. It has its own versions of mass, force, and momentum, but it requires a complete paradigm shift in how we view and measure movement. It fundamentally breaks our normal, intuitive grasp of speed.
Think about an airplane flying through the sky. That is classic translational motion. If the airplane is cruising at 500 miles an hour, the nose of the airplane is moving at 500 miles an hour.
Of course.
But so is the tail and the wings. Every single rivet and piece of glass on that plane is moving at the exact same linear speed.
But now, apply that logic to a spinning wheel, where the center axle is bolted firmly to a wall. Can you point to that wheel and say, the wheel is spinning at 10 miles an hour?
You can't, because different physical parts of the wheel are moving at entirely different speeds depending on where you look.
Exactly. A speck of dirt on the absolute outer rim of the tire is flying in a massive circle, moving incredibly fast. But a speck of dirt halfway down a spoke toward the center is moving much slower because it's tracing a much smaller circle in the exact same amount of time.
That makes total sense.
And the exact microscopic dead center of the axle, it isn't moving through space at all. It is perfectly motionless while the rest of the wheel blurs around it.
So saying a wheel moves at X meters per second is a completely meaningless statement unless you specify exactly which millimeter of the wheel you are talking about.
Pretty much.
Which sounds like a total measurement nightmare for a physicist.
Here's where it gets really interesting. How do you mathematically measure the speed of something where every single atom is moving at a different velocity?
You need to invent a method of measurement that applies to the entire rotating body all at once, as a unified system. Even though the individual points are moving at wildly different linear speeds, there is one critical thing they all share. Every single point on that wheel completes one full 360-degree revolution in the exact same amount of time.
Right.
The wheel rotates as one solid piece.
If the fast-moving outer rim takes exactly 1 second to go all the way around, the slower-moving inner spokes also take exactly 1 second to complete their tiny circle. So physicists stop talking about linear distance over time, and they start talking about angles over time. This is called angular speed. In everyday life, you might measure this in revolutions per minute RPMs, which is how we measure car engines.
Sure.
Or you could measure it in degrees per second. A full circle is 360 degrees. So an engine idling at 60 RPMs is completing 1 revolution per second, which means it has an angular speed of 360 degrees per second.
That makes intuitive sense. But physicists don't generally use degrees or RPMs in their calculations. They use a unit called a radian. Now, I remember hearing the word radian in high school geometry and my eyes completely glazing over. What exactly is a radian, and why is it the native language of rotational physics?
A radian is actually a physically beautiful concept if you visualize it properly. Imagine drawing a circle on the ground. Now look at the radius of that circle, the straight line distance from the exact center to the outer edge. Imagine that radius is a physical piece of bright red string.
Okay, I have my straight piece of red radius string.
Now take that straight piece of string and lay it perfectly flat along the curved outer edge of the circle. Bend it to match the curve. The slice of the pie, the angle that string creates from the center of the circle out to its edges, is exactly 1 radian.
So a radian isn't an arbitrary number like 360 degrees. It's an angle based directly physically on the size of the circle's own radius.
Yes, and because the mathematical circumference of any circle is 2 times pi times the radius, it takes exactly 2 times pi of those red strings to go all the way around the edge.
Okay, doing the math in my head.
2 times pi is roughly 6.28. So there are about 6.28 radians in a full circle. If you divide 360 degrees by 2 pi, you find that 1 radian equals a very clunky, roughly 57.3 degrees.
Okay, but why use this weird 57.3 degree chunk? Why not just stick to nice, neat 360 degrees? It seems like making things overly complicated.
It seems complicated until you try to connect the spinning world back to the straight line world. Physicists use a symbol for angular velocity, the Greek letter omega. Now, let's say you want to know the actual linear straight line velocity, the v, of any specific point on that spinning wheel.
Right, how fast that one point is moving.
The equation is incredibly elegant. $Vel equals the distance from the center, multiplied by the angular velocity.
That is incredibly clean and simple.
But here's the secret. That clean, beautiful equation only works if your omega is measured in radians. Because a radian is literally defined by the radius. If the wheel is spinning at an angular velocity of 1 radian per second, then a point on the rim travels a linear distance equal to exactly 1 radius every single second.
Oh.
The math perfectly seamlessly aligns without any extra conversion factors. If you try to use degrees, the equation would have to be $Vel equals 1 by 57.3. It becomes clunky and ugly. Radians allow the relationships between spinning and straight lines to be expressed with maximum frictionless simplicity.
The universe rewards us when we speak its native language. If you use radians, the math just melts into place.
Okay, so $Vine equals omega. Let's translate that into a physical feeling. If I am standing on a spinning playground merry-go-round right in the center holding the middle pole, my distance from the center is almost 0. So my linear speed is almost 0. I'm just slowly turning around in place.
But if you let go of the pole and walk outward toward the edge of the merry-go-round, your R is rapidly increasing.
Right.
If you double your distance from the center, your linear velocity literally doubles, even though the merry-go-round itself is spinning at the exact same constant RPM.
I physically feel the wind rushing past my face twice as fast, and it becomes twice as hard to hold on simply because I moved outward and increased my radius.
Precisely. You are experiencing $Vi increase the Grega Hill in your own body.
So that covers how we measure a spin once it's happening. But how do we actually cause a spin in the first place? If I want to make a heavy box move in a straight line across the floor, I just push it. I apply force. But how do I push something into a spin? You need a special application of force. This introduces the concept of torque.
Torque. So think about a long, flat wooden rod resting on a table. Let's say you take a nail and drive it loosely through one end of the rod down into the table. So one end is securely fixed, acting as a pivot, but the rest of the rod can swing freely around that nail.
If you press your finger directly against the head of the nail and apply force, what happens?
Nothing happens. The rod doesn't move. You are just wasting effort pushing against the immovable pivot point.
But if you move your hand all the way to the far unnailed end of the rod, far away from the pivot, and you push it with the exact same amount of force,
the rod easily and rapidly swings around in a wide circle.
Exactly. You apply the exact same amount of muscular effort, but you get a totally different physical result simply based on where you applied the push.
That rotational pushing capability is called torque. Physicists symbolize it with the Greek letter tau. And the formula mirrors our angular velocity formula in its simplicity. Torque equals force multiplied by the distance from the pivot point. The distance is a lever arm. The further away from the fixed pivot point you apply your force, the dramatically greater the resulting torque.
It's the exact sensation of trying to open a heavy door. If you push the door right near the hinges, it is incredibly difficult to open. You have almost no lever arm, so you generate almost no torque. But if you push at the handle, far away from the hinges, the door swings open easily. You maximized your distance, maximizing your torque.
That is a perfect physical analogy. Torque makes complete intuitive sense when an object is nailed down or attached to hinges. But what about objects flying freely through the air? There is no nail. There is no fixed pivot point. Why do objects like footballs, baseballs, or even a tossed hammer naturally spin when you throw them?
This requires introducing one of the most conceptually elegant ideas in mechanics. The center of mass and its very close sibling, the center of gravity.
I've heard those phrases used interchangeably, but how do they dictate why a thrown object spins?
In the purely theoretical realm, physicists love to simplify problems by imagining point masses, objects that contain mass but take up absolutely zero physical volume, just a single, infinitely microscopic dot. A point mass can only ever move in straight lines because it has no dimensions. There is no edge to push against to make it spin.
But in the real, messy universe, everything takes up volume. A football has a distinct, elongated shape. A hammer is incredibly lopsided.
Yes, real physical bodies have extension in space. But it turns out, under the laws of physics, real bodies behave dynamically, as if every single ounce of their mass were magically concentrated at one specific, invisible mathematical coordinate.
The center of mass.
That invisible point is the center of mass. For a perfectly symmetrical object of uniform density, like a solid billiard ball, the center of mass sits exactly dead in the geometric center. For a hammer, it sits very close to the heavy iron head.
So how does this invisible point explain the spinning football?
Because if you manage to apply a force that points directly, flawlessly, through the exact center of mass of an object, that object will fly through the air in a perfectly straight, purely translational line. It will not spin even a fraction of a degree.
Really?
Yes. But it is incredibly, vanishingly difficult for a human hand to deliver a force perfectly through the invisible center of mass of a clunky extending object like a football.
So if my hand is even a single millimeter off center when I release the ball,
that tiny millimeter off-center push creates a physical distance between the line of your force and the center of mass. You now have a force and you have a distance. You have accidentally created a lever arm. You have generated torque.
and torque induces a spin.
Yes, that torque induces an unavoidable, immediate spin around the center of mass as the object leaves your hand. That is why nearly everything we throw uncontrollably spins. It is virtually impossible in the real world to push something without creating at least a microscopic bit of torque.
The manuscript provides a truly mind-blowing example of the center of mass in action that just paints an incredible picture. It's the exploding artillery shell in space. I want you listening to really picture the scenario because it plays out like a high-speed camera shot in an action movie.
It's a great visual.
Imagine a heavy artillery shell or a missile flying through the sky in a perfect, smooth, parabolic arc. Gravity is pulling it down, its momentum is carrying it forward. It's tracing a flawless mathematical curve against the sky.
Now, right at the apex of its flight, a timer goes off and it explodes. A massive, violent detonation. Shards of jagged metal casing, shrapnel, and expanding chemical gases hurl violently in absolutely every conceivable direction. It is total, unpredictable chaos in the sky.
According to Newton's first law, an object in motion stays in its motion unless acted on by an outside force. But now we have 1,000 jagged fragments flying in different directions at wildly different speeds. Did the fundamental laws of physics just break down inside that explosion?
Not at all. Because the violent explosion is entirely an internal force. It was produced from within the bounds of the system itself. The only outside force acting on the shell gravity hasn't changed its constant downward pull. So what actually happens to the trajectory?
The outcome here genuinely gave me a sense of awe about how mathematics governs reality.
The center of mass of the entire system, that invisible mathematical average point of all the metal and gas, continues flying smoothly along that exact same original parabolic path, entirely unbothered by the sheer chaos of the explosion happening around it.
The center of mass acts like an untouchable ghost.
It truly does. Because linear momentum is strictly conserved, every single heavy fragment blown violently to the left is perfectly mathematically balanced by fragments blown violently to the right. Every piece blown upward is balanced by a piece blown downward.
So it all just zeroes out.
Exactly. If you calculate the vector sums of all those thousands of chaotic, violent trajectories, they perfectly cancel each other out to exactly zero. So the invisible center of mass just keeps coasting along its serene arc, falling gracefully toward the Earth, as if the explosion never even happened. The unbreakable laws of motion apply rigidly to the system as a whole, no matter how chaotic the internal parts behave.
The chaos of the explosion is ultimately an illusion. The ledger is perfectly balanced, quietly guiding that invisible ghost point forward. Let's bring the center of mass back down to our everyday, stationary lives. The principles of the center of mass directly govern physical stability. Why are some things incredibly easy to knock over, while other things feel almost glued to the floor?
This brings in the center of gravity. On the surface of the Earth, the center of gravity and the center of mass are essentially the exact same coordinate. Gravity is pulling downward on every single individual atom of an object, but structurally, it behaves as if it's pulling downward via a single string attached only to that center of gravity point.
Think about a standard masonry brick. If you lay the brick flat on its wide broadside, it is incredibly stable. You can push it, and it just slides. But if you stand that exact same brick up tall on its narrow end, it becomes wobbly. A light tap will knock it over. Why the difference?
Visualize the invisible center of gravity floating inside the brick. Gravity is pulling a straight vertical line down from that point toward the floor. As long as that straight downward line falls somewhere inside the physical footprint, the base of the brick resting on the table, the brick remains stable.
Makes sense.
If you tip the brick slightly, gravity will just yank the center of gravity back down, snapping the brick flat against the table.
But if I stand the brick up tall and tip it far enough,
Eventually, because the base is so narrow, you tip it just far enough that the center of gravity horizontally crosses over the outside edge of the base. The straight downward line of gravity is now pointing at empty air outside the brick's footprint.
I see.
The very microscopic moment that threshold is crossed, gravity pulls the center of gravity downward, and the brick has nothing underneath to support it. It violently flops over onto its side.
So physical stability is entirely about keeping your center of gravity vertically stacked over your physical base.
Exactly. The wider your physical base, or the lower to the ground your center of gravity sits, the further you have to violently tip an object before that center point crosses the edge of the base. This perfectly explains why a bottom-heavy object is so notoriously hard to knock over. The center of gravity is hovering so low to the floor, you'd have to tip the object almost completely horizontal to get the center of gravity to fall outside the baseline.
It explains those inflatable, bottom-heavy children's punching toys. You punch them down to the floor and they immediately pop right back up to attention. We find it surprising because we are used to objects having uniform density. But the toy is heavily weighted at the bottom. All its mass is in the base. The center of gravity is practically touching the carpet. You can't knock it over because you can't get the center of gravity past the edge.
The center of gravity also perfectly strips away the magic of a skilled juggler or acrobat.
Yes. Paint this picture for us because it changes how you watch a circus.
Imagine a juggler balancing a long wooden cone, perfectly upside down, resting entirely on its sharp, tiny point on their chin or the tip of their finger.
That looks physically impossible. The base of the object is just a single point.
It is technically mathematically possible to balance it perfectly still, but only if the center of gravity high up in the cone is precisely, flawlessly aligned vertically over that microscopic point. But in the real world, the slightest breath of air, the beating of the juggler's heart, will push it a millimeter out of alignment, and gravity will instantly try to yank it down. So what does the juggler actually do to keep it up?
They move.
Exactly. The juggler's secret isn't some mystical defiance of gravity. The juggler is constantly, rapidly moving their body, darting their hand or their chin back and forth, to physically slide that tiny pointed base directly back underneath the falling center of gravity.
Wow.
Every time the top-heavy cone starts to tip, they quickly scoot the base right under it to catch it. They are just manually, furiously keeping the center of gravity over the base in real time.
Understanding the physics strips away the magic, but it somehow makes the actual physical skill involved even cooler to appreciate. We have covered the strict ledger of straight-line motion, and we have covered how to induce a spin with torque, levers, and the center of mass. This brings us to the final, massive piece of the mechanical puzzle. We are going to look at the conservation of angular momentum.
And this is the point where rotational motion gets deeply, wonderfully weird and completely counterintuitive, because it differs from straight-line translational motion in a very specific structural way.
In straight-line motion, inertia, the resistance to changing your speed, depends strictly and only on mass. A 10-kilogram block of iron is a 10-kilogram block of iron. It takes the exact same amount of muscular force to stop it from sliding, whether it's shaped like a compact sphere, a long thin pole, or flattened into a wide pancake. Only the raw amount of mass matters.
Right. But for objects that are spinning, that rule goes completely out the window. How the physical mass is distributed through space changes absolutely everything about how it spins. This critical concept is called the moment of inertia.
Moment of inertia. In rotational motion, this is the functional equivalent of mass.
Exactly. The moment of inertia, symbolized by the letter I, equals the mass of the object multiplied by the square of its distance from the center of rotation. Mass times r squared.
Mass times r squared. Let's really drill down on why that distance, the r, matters so incredibly much more than the mass itself.
Consider a physical body made of 1,000 small, heavy subunits of equal weight. If they're moving down a highway in a straight line, it doesn't matter how you arrange the 1,000 pieces in the truck. The mass is the mass.
But if you take those 1,000 heavy pieces and arrange them into a spinning wheel,
if they are spinning, the placement changes the physics. The pieces glued very close to the center axis of rotation have a very small radius, a small r. So their individual contribution to the total mass times r squared is tiny. But the pieces glued far out on the outer rim have a very large r.
And because r is squared.
Because r is squared in the formula, those faraway pieces contribute a staggeringly massive amount to the total moment of inertia of the wheel.
Let me compare two physical objects to make sure this connects. I have a solid compact sphere, like a heavy bowling ball, that weighs exactly 10 pounds. And right next to it, I have a hollow sphere, like a basketball forged out of heavy metal, that also weighs exactly 10 pounds.
They weigh the exact same. Their total mass is identical when you put them on a scale.
But structurally, inside the hollow metal basketball, there is absolutely no mass in the center. All the metal, all the mass has been pushed far away from the center, out to the thin outer shell.
Exactly. By structurally pushing all the mass to the outer rim, you have massively increased the average distance r of those metal particles from the center axis. And since r is mathematically squared, the moment of inertia of the hollow sphere is enormously, undeniably larger than the compact solid sphere, even though they weigh the exact same on a scale.
Translating that into a physical sensation, think about swinging a sledgehammer. If you hold the hammer by the heavy iron head and swing the light wooden handle in a circle, it's incredibly easy. The heavy mass is close to the pivot point in your hand. Small r, small moment of inertia. But if you hold the wooden handle and try to swing the heavy iron head in a circle, it is exhausting. The heavy mass is far away. Massive r, massive moment of inertia. It resists your spin.
That is the perfect visceral translation. It takes vastly more torque, more physical rotational effort to start the hollow sphere or the hammerhead spinning, and vastly more effort to stop it once it gets going compared to the solid sphere.
This dictates how we build machines. Gyroscopes and the heavy flywheels inside engines are intentionally built with thick, massive outer rims and completely hollow or very light, thin-spoked interiors. Engineers want to maximize the moment of inertia to make the engine fiercely resist changes in its spin and keep the vehicle stable without adding thousands of pounds of unnecessary dead weight to the car.
It is brilliant mechanical engineering based entirely on exploiting the mathematical reality of r squared. So if rotational motion has its own unique version of mass, the moment of inertia, does it have its own version of momentum?
It must.
It absolutely does. And this leads to the grand finale of the universal ledger. Just as straight-line momentum is fiercely conserved, experimentation proves there is an unbreakable law of conservation of angular momentum.
The rule is strict. The total angular momentum of an isolated spinning system of bodies remains absolutely constant.
Translational momentum was mass times velocity. Angular momentum simply substitutes the rotational equivalence. It is the moment of inertia multiplied by the angular velocity, a times omega.
And this mathematical product, E times omega, cannot change unless an outside physical torque violently interferes with the system.
Correct. But here is the loophole that produces the most incredible, counterintuitive, real-world physical effects. We just established that you can change I, the moment of inertia, without changing your actual body weight, simply by moving your mass closer to or further from your center of rotation.
Okay, so if the total product of I times omega is a constant, universally locked number, and I suddenly find a physical way to make my I much smaller, then the universe is forced to make my omega much bigger to compensate.
Exactly. If you want two numbers to always multiply to equal 24, and you start with 8 times 3, if you decide to manipulate the 8 and shrink it down to 4, you're absolutely mathematically forced to increase the 3 up to a 6, because 4 times 6 still perfectly equals 24.
Put yourself in a physical scenario to truly feel how bizarre this is. Picture yourself standing dead center on a perfectly smooth, frictionless spinning turntable. You are holding heavy iron dumbbells in both hands with your arms stretched straight out to your sides.
Let's analyze your body's physical state. The axis of rotation runs vertically right down the center of your skull to your feet. Your arms are fully extended, meaning you have heavy iron weights held far away from the axis. Your R is physically huge. Therefore, your moment of inertia, your I, is massive.
And the turntable is spinning me around at a slow, lazy, angular velocity.
Now, without stepping off the turntable, without pushing off anything, you simply use your muscles to violently yank the heavy dumbbells inward, pulling your arms in, tightly crossing your chest.
I am bringing all that heavy mass extremely close to the center axis. I am drastically, rapidly shrinking my R.
And by shrinking R, you are massively reducing your moment of inertia height. But the universe strictly forbids your total angular momentum from dropping. The universal ledger must balance to the exact decimal. So, because your I dropped, the universe violently, instantaneously forces your angular velocity, your omega, to skyrocket.
Without pushing off anything, the turntable suddenly, rapidly speeds up. I blur into a dizzying spin.
You spin phenomenally faster. And if you get dizzy and push your arms back out wide, your I surges back up and your spin instantly, magically slows back down to a lazy crawl.
This is the exact literal physics of an Olympic figure skater. When you watch a skater go into a dramatic spin on the ice, they always start with their arms and one heavy leg extended far out. They're spinning somewhat slowly, but then they pull their leg and arms incredibly tight to their core, and they instantly become an absolute dizzying blur of speed.
If we connect this to the bigger picture, they are mechanically hacking the universe. They're consciously manipulating their moment of inertia to exploit the unbreakable conservation of angular momentum. It is pure, applied theoretical physics rendered in beautiful motion on the ice.
It is stunning to watch once you know the hidden math they're exploiting, but there is a flip side to this spinning ledger, a hard limitation. And this is where we see the impenetrable wall between these two ledgers of motion.
Yes, the universe is very strict about keeping its ledgers separate. A body that possesses only angular spinning momentum cannot miraculously transmit an unbalanced straight-line translational momentum to another body.
In plain English, spinning rotational momentum cannot magically turn itself into straight-line forward momentum just because it wants to.
Right. It absolutely requires a physical mediator to bridge the gap. It requires friction.
Think about a frustrating winter experience that anyone in a snowy climate has felt in their bones. You are sitting in your car, and your tires are stuck on a perfectly smooth, frictionless sheet of black ice.
You press your foot down on the gas pedal. The engine roars and generates immense power. It applies massive torque to the heavy steel axles. The rubber wheels spin beautifully and violently. You have successfully generated an enormous amount of angular momentum in those spinning wheels.
But the heavy car doesn't budge an inch. It just sits there, wheels screaming, spinning vainly. Why?
Because to actually move the heavy car forward, to gain translational straight-line momentum, the car must physically transmit an equal and opposite translational momentum backward into the Earth. That's Newton's third law. The tire pushes the planet backward, the planet pushes the car forward.
But because there is absolutely zero friction between the rubber and the smooth ice.
Because there is no friction,
Yeah.
the rapidly turning wheel cannot physically grab the surface of the Earth. It cannot grip the planet to push it backward. And if the car cannot give the Earth negative backward momentum, the universe strictly forbids the car from receiving positive forward momentum.
Yeah, it's totally trapped.
The massive rotational energy of the wheels is completely isolated in its own spinning ledger. It cannot bridge the gap to become translational motion without the physical friction of the asphalt acting as the required translator between the two separate ledgers.
The wheels just scream and spin, and the car stays perfectly, frustratingly still. It's a brutal, practical reminder from the laws of physics that you can generate all the rotational energy in the world, but without a physical connection to the environment, you aren't going anywhere.
It is the universal ledger enforcing its rules indifferently, silently, and perfectly.
And what an incredible journey through those silent rules this has been. We started by looking at the strict accounting of two simple hockey pucks colliding on the ice, proving that motion is never lost.
Never.
We uncovered the unbelievable reality that the massive planet Earth literally falls upward to meet your dropped keys. We tracked the ghost-like mathematical center of mass, guiding a violently exploding shell serenely through the sky. And finally, we decoded exactly why a figure skater blurs into a dizzying spin simply by crossing their arms.
We set out with the mission to prove that the chaos of the physical world is ultimately an illusion. Behind every violent collision, every unpredictable bounce, every chaotic spin, there is an elegant mathematical ledger of mass, radius, and velocity. And that ledger always balances perfectly to zero.
The universe is a flawless accountant. And as we wrap up this deep dive, we want to leave you with one final provocative thought to ponder as you move through your physical day. a thought that scales up that idea of the Earth moving when you drop your keys.
Based on the absolute, unbreakable law of conservation of momentum, consider what mathematically happens every single time you take a simple step forward.
Okay.
When you stand up from your chair and walk from your living room into your kitchen, your physical body gains forward momentum. To balance the universal ledger, your feet physically pushing against the floorboards must impart an equal and opposite physical reaction down into the foundation and ultimately onto the entire planet.
Wait, you are literally physically pushing the planet backward with every step.
Yes. Every single step you take down the sidewalk, every time you sprint for a bus, even every time you wildly wave your arms in the air, you are microscopically altering the rotational speed and the orbital trajectory of the massive globe you stand on.
That is just, it's hard to wrap your head around.
Your localized, seemingly insignificant daily physical existence is mechanically, mathematically, and permanently linked to the movement of the entire planet Earth. The chaos you think you see around you isn't chaos at all. You are deeply physically tethered to the unbreakable ledger of the universe.
Think about your connection to the planet the next time you walk down a busy city street. Thank you for joining us on this deep dive into the hidden rules of reality. Look at the spinning, colliding, moving world around you today with fresh eyes. And remember, no matter how chaotic it looks, the ledger is always balanced. See you next time.